and welcome to our webinar, The Faces of COVID-19. This webinar is part of a series by uCalgary experts to support our community through this COVID-19 pandemic. My name is Deborah Yedlin. I'm the Chancellor of the University of Calgary, and I'm going to be your moderator for today. Please submit your questions using the Q&A button at the bottom of your screen, and we'll get to as many of your questions as we can during the session. And if you do have to leave early, don't worry, it's going to be online and you'll be able to look at it as your schedule permits. So today we have two professors, scientists from uCalgary who will be presenting to us. The first is Guido van Marl. He's a PhD in molecular virologist and associate professor in the Department of Microbiology, Immunology, and Infectious Diseases. And Chris Modi is a clinician, scientist, and professor and head of the Department of Microbiology, Immunology, and Infectious Diseases at the University of Calgary. They both have very interesting insights to share on the issue that we're all facing around the world. And what I'm going to do is ask Guido to start the presentation, and then Chris will follow, and then we'll have Q&A, and we'll try to make this as interactive as we possibly can. So Guido, if I could, I'm sending it over to you to start your presentation.
As said, I'm Dr. Guido van Marl. I'm in the Microbiology, Immunology, and Infectious Diseases at the Snyder Institute and the Cummings School of Medicine. I'm, as said, a molecular virologist, so I study viruses on their little molecular level. I actually did my PhD on coronaviruses before there was any SARS, and the interesting question I always got from people was, why do you study a virus that only causes the common cold? And I guess with a SARS outbreak, MERS, and some of the current things, it shows that a lot of basic science that we do because is of use, as a lot of the information that colleagues that have been working on these viruses for many years are now using to tackle this virus. So novel coronavirus in the news, you've seen it in first as a date as novel coronavirus 2019. Now it's called COVID-19, or that's the name of the disease. But the scientific name of the virus is SARS coronavirus type 2. As it is related to the SARS coronavirus that we saw in 2005. These are actually the electron microscope pictures from the first cases that were reported by the Chinese scientists and clinicians in the New England Journal of Medicine. So just a little bit going down to some fundamentals with regard to infectious diseases or germs, viruses and bacteria we know. But, you know, there are many infectious diseases that cause various diseases, such as the helminths. So basically those are worms, tapeworms, fungi, the viruses and bacteria, but also the protozoa, such things as malaria. In the news, you see a lot that people are using bacteria and viruses in the same vein in many cases. If people talk about E. coli 0157, then sometimes in the line below it, the E. coli is a bacteria, then they say the virus causes blah, 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 severe gastrointestinal disease. To give you a bit of perspective, viruses are small agents versus bacteria that are larger, and actually bacteria are single cells that can replicate and multiply on their own. And we talk about bacterial meningitis, tetanus, diphtheria, and strep throat, but also what we call eukaryotic cells. So those are organisms that have the same type of cell architecture as the cells in our body. So that would be like malaria or fungi like athlete's foot. There's also this special category, the prions, which are these for Creutzfeldt-Jakob disease or mad cow disease. We won't go into those. Viruses come in many shapes and sizes. In general, they're packages of genetic material. They contain genetic material, either DNA or RNA. This is the way we indicate there are some chemical differences between those. but there are packages where they basically have their gene in there and they're delivered to deliver them into the cell. And so we have roughly two classes. One we call sort of the enveloped viruses, and the COVID-19 virus is an enveloped virus. So that's the one you see on the left of your screen, and that has a membrane around made out of lipids. And in that membrane, there's other proteins that stick out, and that's why the virus binds to a cell and mediates entry. Now, that lipid, so it's basically fat. If you disrupt that, you make the virus non-infectious. And so that's where the things like the alcohols, the soaps, and the decontaminants are working on with regard to the current COVID or the current COVID virus. Coronaviruses are a big group of viruses that have been around for a long time. We've been studying them, like I said, for a long time. They're known for veterinary infections, and they belong to a group of many, many other viruses that infect many, many different organisms on the planet. Now, here you see the pictures of the classical coronavirus structure, where we have the spike protein that sticks out on the outside, and that's where you bind to the cell and gets entry. And that's where vaccines are being targeted against and some of the other structural proteins that make up the virus particle. But what is so striking about these viruses under the electron microscope, as you see in the top pictures with A and B, they look like the sun with a halo around it. And that's, the corona of the sun, so the halo around the sun, hence the name coronaviruses. So viruses do not grow on the table. If they're sitting on a surface, they don't do anything. In contrast to bacteria, who can grow on a surface and multiply. A virus needs the cell to multiply. So they infect a cell from a host. That could be a single cell, that could be an intact human being, and they multiply, and either those cells stay alive and spit out virus particles, or they blow up the cell and then release virus particles to infect new cells or different organisms. So how do viruses cause disease? Well, on some simple things, or some simpler way to explain it is, like you saw in the previous picture, if the virus infects the cell and it needs to blow it up to get the virus particle out, that causes damage. And other ways is also that the immune system tries to attack the infected cells and kills them. And if it goes too much, then you get disease and tissue damage. The other thing, and that's also important for the SARS coronavirus 2 or COVID-19, is that the immune system responds and overreacts with what we call cytokines and other molecules. And that creates damage. So that could be resulting in like the pneumonia and also some of the other immune abnormalities that you see in these patients. The other thing too is the virus proteins. So the proteins that the virus produces to make virus particles and to hijack the cells are also toxic. So they kill cells. And then another problem that can be caused by viruses is that your immune system is busy fighting the virus so that other organisms or other pathogens can take advantage of that. And that's cases that happens with influenza, where you get a pneumonia, but it's induced by a bacteria who takes advantage of your weakened immunity. And a thing to understand about viruses, and sounds a bit confusing when you see it comes from different organisms. A virus does not always infect every cell or organism. So one virus might infect a human, but not another animal or another cell, or it might only infect a particular type of cell in a body of an organism. Why are the reasons? It either cannot get in, so it cannot bind to the cells with those things that stick on the virus particle and get in, or even if it gets in, then the cell doesn't have the machinery to actually make the virus replicate. Because the virus is small, it doesn't have all the genetic information, it needs the pieces of the cell to make copies of itself. And if the cell doesn't express those or doesn't have those, the virus cannot replicate. And so there is a tight link between which cells or which organisms and which virus can get in. We call that tropism, so the ability of a virus to infect a particular cell or tissue or host. So there might be some cells, some viruses infect the nervous systems, while others infect the liver in a host. Other thing to realize is that viruses do not always have to cause disease. All the viruses, most of the viruses that we know are the ones that cause disease, but there are many, many viruses out there in the environment that do us no harm at all and actually help life on Earth. So in your compost heap, they help with the composting process too. But yes, viruses can infect indeed different animals, and that's part of their life cycle. And we know about this for influenza viruses, where we know that viruses jump from different species and get new varieties, and that's why we need to always make a new vaccine. So what about coronaviruses then? Well, coronaviruses also have a broad host range. There might not be as extravagant or as maybe the influenzas, although comparisons are always hard to make. But coronaviruses, we know for them as important veterinary pathogens. So it's like infectious bronchitis virus for chickens and a gastrointestinal disease in pigs. And so they infect mammals and avians. Humans, like I said, when I worked on it, when I started in science, we knew about coronaviruses causing the common cold. And the most common ones were 229E, NL63, and OC43. But since 2005, we also know about severe acute respiratory syndrome, or SARS. And then we have, later on, became then Middle Eastern Respiratory Syndrome virus, or MERS. And then now we have SARS coronavirus 2. So, like I said, we had the human coronaviruses such as NL63. They've been with us as far as by studying their genetic material, they're probably 500 to 800 years old in the human population. And then we get some more recent infections where SARS started 16 years ago, MERS about 7 years ago, and currently we have SARS coronavirus 2, or COVID-19 virus. So yes, also coronaviruses jump host, and some of you might remember with SARS, it was first thought that it came straight from the civet cat, but it actually, the original host was probably the bat. And then through the civet cat, it came into the human population. So the virus changes, adapted, and then was able to infect human cells. The same goes for us too, that humans can actually pass things on to animals and also cause disease. To illustrate some of the MERS coronavirus, or the Middle Eastern Respiratory Syndrome virus, we've known about it now for about 7 years, and that came actually through the intermediate host of like dromedaric camels. But the original host is probably, the original source is the bats. And then from bats through camels to humans. And in contrast to SARS coronavirus 2, yes, there is transmission from MERS from human to human, but that seems to be less infectious compared to the new COVID-19 virus. So where does SARS coronavirus 2 or COVID-19 come from? So as soon, thanks to the new technologies that we had, as soon as these, we started to identify these people have determined their genetic material, and they're also screening for many, many viruses in other organisms. And what we found is, yes, it is a coronavirus that is related to SARS, or it has similarities to SARS coronavirus, but it's not identical. I will get to that later. It's also different from MERS coronavirus. As we look at this picture, is basically a family tree, like the tree that you would say from an ancestry.com. We can figure out based on their genetic material how they are related. And so it is very closely related to things that we also find in bats, but it's again not identical. And then now through some newer data, it actually is probably there is a intermediate host, because we find the same viruses in pangolins, and these animals have been traded for their scales because of medicinal reasons that they have, and they've found similar viruses, or viruses that look very similar to the SARS coronavirus 2. Now the question comes up, did we get it from the pangolin, or did the pangolin get it from the same host as we got it? But the people think it might have been come to the pangolin. Other thing to sort of point out is, yes, it is a SARS similarity to SARS, and people have done some more studies on it, and it seems to have a common ancestor. So there is some virus out there that it originated from, but it's not identical to SARS coronavirus. So SARS and this new coronavirus, COVID-19, are different. So it's not a SARS virus that escaped from the lab or was constructed by something else. This is a natural variety of the virus. So what about therapies and vaccines? There's a lot of talk about it, and a lot of things are being tried and tried at the moment. I'm going to go really quickly into this and then hand it over to my colleague, Dr. Modi. But when we take a look at viruses, this is a schematic. The virus gets in, spits its genetic material out, and then goes through these elaborate processes to make copies of itself. A lot of the antiviral therapies or approaches that we are using are trying to block these processes. So we're looking for drugs that block these steps. And we're talking about vaccines, and the vaccines are targeting also against like the structural proteins, the virus particles, so that the antibodies can bind, and so the virus can't get in and infect cells. So we know from other viruses that we make immune responses to these coronaviruses and that they can be protective. We're still working on determining how well those are for the current coronavirus. But so people are working very hard on these type of targets, the same as we would do for sort of like influenza and the other SARS coronaviruses. But we also need to test the safety of the vaccines, of course, and because with SARS, we noticed that the immune response doesn't last that long. So might be an immune response, but over time, you lose your memory, so you might have to revaccinate people if you find it. There's always the things, viruses mutate. Will they potentially mutate and escape the vaccine? Looking at the viral variability, the virus seems to be pretty constant, so not as a rapid changer at the moment. Therapies, actually, people throw on a lot of batteries of experiences that we have. So convalescent serum from patients is being used, basically also because it's been shown, this is an old technique that's been shown in many, many other viral infections. People have used it for Ebola, also with SARS. It's basically taking immune serum from patients that have recovered and give that to critically ill patients. And there is also ways that you can make those things artificially. So that's being tested, and hopefully that's being rolled out quickly. The other things is, like I said, blocking the virus from entering, blocking the virus from multiplying, and people talking about blocking the molecules that make the virus, or what we call a replicate, which we call the replicase, and that's that drug like remdesivir that people are using, and also using protease inhibitors. These are drugs that people have used for HIV as well as other viruses such as Hep C. The other way is modulate the immune response so that it not overreacts, like I said before, so suppressing certain things, or also activating other antiviral responses that cells have to their capability of fighting infections. So that is, in a nutshell, really what is the virus about? What are some of the things we're looking at? And now we would like to hand it over to my colleague, Dr. Modi, who will be talking more about like the epidemiology and some more on vaccines and other areas of interest.
Dr. Modi, if you can go ahead with your presentation.
Thank you. Just see if I can share my screen here, Chancellor.
Hey, there you go.
Is that it?
Yeah.
Okay,
There.
great. Now, just get the electronics to work here. Can you see that?
Yeah, we can see it.
Great. Okay, it's displaying a little funny on mine, but we'll work with it.
There's subtitles
Okay,
here on your as you're speaking,
just a sec here.
translating your speech.
What do you see now?
We see this the slides, and then we see when you speak, it's translated into text at the bottom.
Oh, I see. Okay, so what I want to, so it's not showing the right slide though. It's jumped suddenly to a slide way down. So I'm going to just stop sharing. I'm going to try and get to the right slide.
Maybe we can ask Dr. Van Marl a couple of questions while you're figuring this out. How about that?
Yep,
Sure.
go ahead.
Okay, one of the questions that's come up is why are so many viruses carried and passed on by bats?
So because we're basically looking for it now, because we know about it, but there's many other animals out there that, it's also through birds and other areas, but also because bats fly around, so they spread certain things and there's particular interactions. There's also a lot of ideas about maybe deforestation, that animals start to spread those around. And also because they're mammals. So they're similar to us compared to a bird, because I saw another question about how does it infect the different animals? Yes, so you can, but there is the virus needs to adapt. So as far as we know at this moment in time too, it doesn't look like we can really massively infect other animals with this virus. People are testing that just to confirm, but certain ones, yeah, even though coronaviruses can spread between species or between different organisms, it takes a little bit of adaptation. And some of our viruses, can we pass it on to our dog? It doesn't look, there is some report, but it was very mild case, but that needs to be confirmed further. But that seems to be, there is a hurdle in that too. But also because bats are mammals, we are mammals, so that makes it, it's one less hurdle to jump.
Makes sense. Okay, I think we're ready for Dr. Modi.
All right, Chancellor, can you see the screen that says Faces of COVID-19?
I can.
Excellent. Okay. Well, thank you very much for asking Dr. Van Marl and myself to do this. As you can see, we're both from the same department and from the same institute. So the Department of Microbiology, Immunology, and Infectious Diseases and the Snyder Institute for Chronic Diseases. So I called my talk "The Faces of COVID-19," and I thought I'd start off with a serene note because these are troubling times, and I'm going to present some troubling data. But I really like this picture. It's a picture that I took in Wuhan in 2013. And it's a hillside in China, and it just sets my mind at ease, and I hope it does yours too. So that's one face of we've heard a lot about Wuhan, but maybe not the serene side of Wuhan. Second face of COVID-19 is this one, and this is the one that Dr. Van Marl has been talking about, the virus, how it works and what it does. Another face of COVID-19 is this one. And this is a face that is a little bit scary. This is an intensive care unit in Wuhan. And I hope that we never get to that stage in Calgary or in Alberta. I hope that we never get to the stage that we run out of equipment and supplies as they've done in some European countries, but I'll show you some data about that. This is another face of COVID-19, and it is the face that affects your portfolio and the economy, and why so many people that work for us in government are so concerned about COVID-19. And it just shows the precipitous decline in the stock market over a 3-month period where it was at its high and basically dropped into near recession levels. I guess we'll see whether they call it a recession or not. And this is another face of COVID-19. And this face is unique to the world because it reflects the absolutely unprecedented speed with which information has become available and people have begun to act on that information to make new discoveries and to care for patients. So on the very far left side of the slide, on December 31st, 2019, the World Health Organization was alerted to a pneumonia-like illness in Wuhan. If you scan across to January of the 11th, so we're talking less than 2 weeks, a process that previously would have taken months or even years to accomplish. When we had SARS, it took for sure months to accomplish. This was accomplished in just slightly over 10 days. That is, the entire genetic sequence of COVID-19 was determined and deposited in a database for all to see and to use. By the 21st of January, only 10 days later, we had 2 gel-based assays introduced at the Calgary site to begin diagnosis, and only 6 weeks later, 5 weeks later, the TACMAN assays were available in Calgary and Edmonton to make the diagnosis, and we were ready to see our first patient. So this is, and similar speed is reflected in the literature, where some of the top tier journals made very quick turnaround publications available so that people around the world could be have available free information and keep up to date with the pandemic as it evolved. Well, I got asked to give a talk on COVID-19 the very first time by our dean at the Cummings School of Medicine, Dr. Meddings, Dean Meddings, on February the 12th. And he asked me at about 11 o'clock at night, could I give a talk on COVID-19? And of course I responded yes. And what I did was I went to my computer in my home office and I took this screenshot. And it is a reflection of the what became the pandemic afterwards on that evening. And you can see that the cases are distributed almost exclusively in Canada. There were a few cases in Canada, or almost exclusively in China. There were a few cases in Canada, and 60,000 cases in the world with 1,300 deaths. This is the slide that I took last night. Should actually say the 29th in the title. You can see the date down in the bottom left. And that cases has now expanded to 720,117 with nearly 34,000 deaths. And I didn't pull the slide this morning, but this is a website that's available to everyone. It's updated 3 or 4 times a day, and you can see the pandemic as it evolves in real time by following this map if you choose to do so. So the question is, this is a worldwide phenomenon now, but how are we doing? And really the answer to that is you have to start in China to understand that. So this is the accumulation of cases over time between the when they first started tracking, which was in towards the middle or end of January, until March 17th. And you can see that there was a rapid escalation of cases in China. There was a blip on about February the 12th or so, which was just about the time when I showed you that slide, that was due to a redefinition of cases in China. But basically there was a rapid escalation of cases, and then as you follow the curve towards the right, you can see that it flattens off. And so the question is that what we usually see when we think about pandemics or epidemics of viral illnesses? And the answer is no, it's not. So this is a slide that I took from my television set, and it's when Bruce Alward, who is a Canadian scientist and epidemiologist and works at the World Health Organization, presented his report. He was the lead WHO person who went to China and did the on-site visit there. And during his presentation, he showed this slide. And what it is it's a slide of the number of cases daily in China. And what he pointed out was that the shape of this curve is different than what we would expect in an epidemic. What we expect is what's called a bell curve. And it is that bell curve that we talk about flattening. And he said, this is not a bell curve. It's different than a bell curve. So what I did was I took the slide and I actually drew a bell curve on it. You can draw the bell curve in different ways, and I don't profess this to be the most, the exact way that this bell curve should be drawn, but basically it shows you that during the early part of the epidemic, the number of cases followed this bell curve. The difference between the red line and the blue line is the cases that were avoided in China because of the public health measures that they took. And so that's the number of cases that were saved. And because there is a direct relationship between cases and deaths, it reflects the number of lives that were saved in China. So how does that reflect to what we're seeing in the rest of the world? So in order to understand that, what I did was I superimposed the graph from China, this is the graph that you've previously seen, with the graph from the rest of the world. But in order to do that, I need to shrink the axis of China and then superimpose the rest of the world. So here we're going to shrink the axis to the rest of the, or for China. And here is the rest of the world. So this is what we're now seeing in the rest of the world. And you can see that the early part of the curve is entirely due to cases that were in China. And that is up to around 100,000 cases. The rest of the cases come from the rest of the world. And that is the other over 500,000 cases of COVID-19. So that's what we're dealing with now. So how do we deal with this? Well, people that you watch on the TV often use the words containment and mitigation. And I think there's some mystery amongst the usual person about what containment and mitigation actually are. So let me explain that to you. What containment is basically trying to put the virus back into nature. So get it out of the human population. We're not going to get it out of the bats or the other intermediate animals that Dr. Van Marl talked about, but you're trying to get it out of humans. And so how do you do that? Well, in order to do that, you have to know where it is and then stop transmission from the people that you know have it. And the way that you do that is you test. You test very widely. And everyone, I would wager, everyone in the world needs to be testing more. Once you test, then what you do is you quarantine those people that test positive. You don't allow them to spread it to somebody else. And you do contact tracing. That is to say, all the people that those infected people have come into contact with, you tell them that they need to separate from everyone else so that it breaks the chain of transmission. That's containment, and it can happen on a global level, it can happen on a country level, it can happen on a community level, or a cluster level. And so in, say, for example, in a community setting, that can occur. In a nursing home, it can occur, where you basically contain the virus. Then there's the aspect of mitigation, which is when you don't know where it is. And so if you think about that, when you go to the grocery store, you don't know whether another person in the grocery store has it. So how do you work against that? So basically what you're trying to do is to try to reduce acquisition. And so that means washing your hands after you've touched a public surface. So if there was virus, you wash it and you kill it. You don't touch your face, and that prevents transmission from your hands to the site of inoculation, which is your face. You practice physical distancing. Now, I use the word physical distancing because that's what I'm trying to achieve. I'm trying to achieve that two humans don't get within 2 meters of one another. I actually don't want social distancing. I want people to be socially connected and to be socially in social proximity to one another, but I want them physically distanced. The next way is that you impose travel bans. So if cases are coming into your country, and that has been a significant proportion of the cases in Alberta, then what you do is you repatriate Alberta citizens, Canadian citizens, but you don't allow people in that are from other places, and you don't allow people to travel and come back. And then the last way that you reduce acquisition is you start closing down public businesses, schools, and then you can think about escalating that to the stage of where you basically lock down everything, as we have done in some European countries. And then, of course, if you're sick, even though you don't know what the virus is, you don't know whether or not it's the COVID-19 virus, you isolate. So it doesn't matter whether you have the flu or a rhinovirus or any other virus, you isolate. So you don't know where it is, but you isolate. So those are what we mean by containment and mitigation. So I've been asked, why is COVID-19 so difficult to contain? And I got asked that question one day on a radio broadcast, and I thought, what a wonderful question, because I think there's lots of mystery around that issue. So basically, the way I answered the question was, I said, you really have to get into the weeds a little bit about COVID-19 to understand why it's so difficult to contain. The first is coronaviruses, because they're RNA viruses, they're very prone to mutation. So they're mutating all the time, and it's just part of the nature of the virus that it uses RNA rather than DNA as its genetic material. And COVID-19 has mutated, as Dr. Van Marl talked about. It started off as what we call the S type, and it moved to the L type. And if mutations confer increased transmissibility or virulence, then that would be a problem and potentially explain why COVID-19 was so difficult to contain. It turns out that the mutation events that have occurred in COVID-19 virus have not conferred increased transmissibility or virulence. And so while they've occurred, they have not been bad for us. Well, there will be further mutations, and we need to track this very carefully, because it is a mechanism by which it may become more difficult to control in the future. The second way that makes COVID-19 difficult to control is asymptomatic transmission. And there has been a lot of talk about asymptomatic transmission. Does it actually occur? Does it not occur? And the World Health Organization came out a few weeks ago and they said asymptomatic transmission is very rare. Less than 1% of the people that the world has tested have viral titers high enough that they could transmit the virus. We don't really have very great data about asymptomatic transmission, and furthermore, the data has been troubled by some misinformation in the literature. So one of the very first cases that was reported where a Chinese woman went to business meetings in Germany and was reported to be asymptomatic, and then the members in that meeting got infected, turned out not to be true when it came out that the woman that visited Germany did actually have a fever, was taking maximum doses of acetaminophen, and was in no way asymptomatic. There's a more recent report that came out last week, and it tracked cases moving from one city to another city in China during the early part of the outbreak. That I looked at that case report very, very carefully, and it might be that there was asymptomatic transmission, but there are other ways to explain it. So I think some of the best data that we have is data like this. So this is what is the viral load in respiratory secretions from people at the day that they become symptomatic. And you can see that from this curve that this is time of from onset of symptoms on the horizontal axis and the viral load on the vertical axis. And you can see that the peak viral load is actually on the day that they're diagnosed. Well, it takes a little while to accumulate that viral load. So that means that they probably were infectious a day or two prior to becoming symptomatic. And so there probably is some asymptomatic transmission. How big a problem it is, I don't know that it's a big problem, but it is a concern, because a strategy that says if you're if you're sick, stay home, it means that it is possible to transmit the virus a day or two before you actually become sick. And so measures that include social distancing, all of the mitigation strategies that I mentioned become important. The third way that COVID-19 is so difficult to contain is based on the transmission rate. And here in this slide, you can see that one person transmits the virus, statistically at least, to 3. Those 3 then transmit, each one of them then transmits it to 3. And you can see that there's an rapid escalation in the number of cases. This is what we call the transmission rate, sometimes called the attack rate, sometimes called the R0 or R factor. And we'll come back to that. But that is a high number, 3. So to put that in perspective, I show this slide. So the R0 is along the horizontal axis. And in this slide, and fatality rate is based on the top, but in terms of controlling it, we're interested in the R0. So you can see that the sort of red star there in the middle is about where the COVID-19 virus is. It's about 2 to 3. And the red circle towards the bottom left is seasonal flu. It's about 1. One person transmits it to one other. COVID-19 is 2 or 3. And then over on the far right, just below the circle that says spreads faster, we have measles. Measles spreads with 15. And so that's why recent outbreaks of measles have been such concern. So COVID-19 is a pretty good spreader, okay? Not as good as chickenpox, right along the bottom, not as good as measles, but it's significantly better than seasonal flu. So how does it compare to other respiratory virus pandemics that we've seen. So I don't think anybody in the audience remembers when the 1918 influenza pandemic came to Alberta. But this is a slide of the operators at the Alberta government telephones all wearing their masks during the 1918 influenza pandemic in Alberta. So just to review, at the top on the left, the case fatality rate for seasonal flu is about 0.1%. That means that 0.1% of people that get infected die. Approximately 500,000 people per year die of the flu. That's worldwide, and it varies a lot depending on the particular strain of influenza that's circulating that year. And in Alberta, between 150 and 300 people die each year. The 1918 pandemic, the case fatality rate was 5%. And that 5% translated into 50 million people in the world, and 4,000 Albertans died. So that's a case fatality of 5. The case fatality from COVID-19 virus right now worldwide is somewhere around 2 to 3%. So it's not as bad as the 1918 flu, but 10 to 20 times worse than seasonal flu. So how many deaths are going to occur from COVID-19? We don't know. How many deaths in Alberta? We don't know. But it's certainly concerning when Anthony Fauci, the head of the National Institutes for Allergy and Infectious Disease in the United States, indicated over the weekend that 100 to 200,000 deaths in the United States would be a conservative estimate of what the mortality in the US is going to be. So is physical distancing and mitigation important? Let me tell you a little bit about that. So this is the this is the actual number of cases that have occurred in Alberta up until last night. So if you look at that curve, you can see that the curve is gradually increasing in its rate. And what that means is that the number of people diagnosed with COVID-19, confirmed with laboratory tests, is doubling every 5 days. So that means every 5 days, there starts with 1, it goes to 2, it goes to 4, to 8, to 16, to 32. And so last night we had 661 cases, as I'm sure most of you know. That's a doubling of every 5 days. So you can take that data and you can extrapolate that data into the future and say, what is the future going to bring? What's going to happen over the next month? And that's represented on this curve. So you can see, so this predicts what's going to happen in Alberta out to the 28th of April 2020. Beyond that, it's very difficult to predict what's going to happen because a lot of factors could influence this. So that curve, this curve, was done before last night, and it predicted that as of today's date, we would have 500 cases. It turns out we don't have 500 cases, we have 661. That means we're ahead of the curve, we're not behind. Ahead being bad. If you follow that curve, by April 28th, we will have 27,000 cases of COVID-19 in the province of Alberta by the end of April. We will have 4,100 hospitalizations, and we will have 1,400 ICU admissions. Okay, well, what would happen if our containment and mitigation strategies are successful? Here's what the curve looks like. So if we take that doubling time of 5 days and all the efforts that all of Albertans take can reduce that doubling time to 7 days. That doesn't seem like very much, but it's going to take a supreme effort to reduce the doubling time to 7 days. If we do that, we can reduce the number of cases from 27,000 to 8,800. We can reduce the number of hospitalizations from 4,100 to 1,300. We can reduce the number of ICU bed admissions to 431. And I can tell you that 431 ICU admissions, 1,300 hospitalizations, we might be able to handle that in Alberta with the available bed space and medical staff that are available. It will be a stretch to reach those targets, 1,300 hospitalizations and 431 ICU admissions, but we think we can do it. It will be difficult. We cannot handle it if their doubling time continues at 5 days. So with that, I would say, sorry. I'm going to paraphrase Sir Winston Churchill by saying, I'll let you read it.
Thank you, Dr. Modi. I think we all have to take the words of Winston Churchill and your presentation very seriously.
Thank you. So with that, I've tried to cover some of the phases of COVID-19, the virology, some aspects of public health, the economy, the speed and data has changed the world, and finally, I hope I'm thanking everybody for their contributions.
So as you can imagine, we have a lot of questions. We're not going to get through them at all, but I think the question everybody's probably sitting and wondering about is, when you talk about significantly decreasing the rate of spread, what do we do? Is it enough that we're doing now in terms of the isolation, the social distancing, minimizing contact, or do we need to think about something else in terms of slowing the doubling from 5 days to 7 days?
Right. So it's a good question, Chancellor, and I think that the answer is that that probably more restrictions are going to come our way. And I think the reason for that is because the things that we do today will be reflected 2 or 3 weeks down the road. So the things that we were doing 2 or 3 weeks ago are reflected in the numbers that we have now. And so the number of cases is going to continue to escalate for a while. We need to flatten that curve, as I've indicated, but I think that there's going to be more and more pressure on the Minister of Health, the public health officers, and by the public to have more restrictions so that we can slow this epidemic. So I think we're going to see more.
Do we need to think about isolating specifically at-risk populations?
I don't think that that's the way to go. If what we're talking about is isolating vulnerable populations, I don't think that that's the way to go. I think the way to go is to make changes at a population level or individual segments of population. I think we want to make a change uniform right across. And so, we've seen increasing restrictions in terms of sizes of gatherings, and I suspect that that will become more and more, until we're down to just household contacts. And then, hopefully, hopefully in Alberta we won't get to the stage where we need to impose a complete lockdown. But I think it's going to be tough go over the next 2 or 3 weeks.
When you look at the rapidity at which we've been able to sequence the DNA of the virus, we have computing power that we didn't have when we were looking at SARS. So are you optimistic from that perspective that we'll be able to find a vaccine in much faster, time scale than we have in the past?
So yes, so the technology is, it's a game changer. What we know now about this virus compared to where we were in SARS, we're ahead of the game. We also learned from SARS and from MERS and all the other ones. And so what we know, so we actually can almost track it as things happen. So you really can anticipate that, and also figuring out which other parts of the virus we can target. So yes, I'm very, very hopeful with those things. That is a game changer. That is like awesome.
There's a question about testing being limited, and your conversation about testing more widely. Is there a balance point where we sort of get diminishing marginal returns if you increase testing, or is this something that we actually should be suggesting or putting pressure on the government to test more widely than we are already doing it now?
Well, so as you know, last week they changed the testing criteria, and so because of the limited availability of tests, they restricted testing to healthcare workers, because we have to maintain healthcare workers to be able to look after the surge of patients that's coming, and also testing travelers, because they're at least in Alberta, they are the most significant source of cases in Alberta. And so there's a balance between availability of tests and testing the highest risk group, or the group that you want to maintain to be able to provide care. The group that we're missing is the close contacts. And so if you look at the number of close contacts, it basically rivals the number of people that have traveled and returned to Alberta. And so there's that whole segment that we're not able to test because because of the criteria, and the criteria are set up because of availability of tests. So we need to be testing that population at the very least.
So your charts show the SARS having similar spreadability rate as COVID, but a much higher fatality rate. And the question is, this individual doesn't recall a large global physical distancing response with respect to SARS. Why is physical distancing response globally so large today versus SARS? What makes that SARS virus different than the COVID in terms of its spreadability?
Guido, you want that?
Yeah, okay. So the difference here is also that with the SARS, we were on top of it. We probably responded faster because it had a more significant disease. And it's also the disease onset is quicker, so it's easier to spot patients who are actually ill and then contain them like that. So that is also the same what people think also with MERS, having less spreadability versus earlier disease onset. So it's easier to catch patients and then basically contain it. And so that's, that's the difference between the two agents. That there might be more people, it takes longer for you to develop disease. And so somebody may be infectable before that or whatever. But yeah, it was just the speed and the severity with it. So that woke us up probably earlier to clamp on it much more aggressively than we have been able to do now. Although we do now very aggressively.
Unfortunately, we're just past 1 o'clock, and I'm going to have to wrap this up now. I want to thank everybody for being here and listening to our webinar. We will be posting, we're going to see if we can respond to some of the questions in a different way so that everybody can have access and see some of their answers posted online. Thanks very much and stay healthy.
Thanks for asking us.